Okay, in section 9.3, we're graphing general rational functions. So you've already learned how to graph simple rational functions, which involved finding a single vertical asymptote and a single horizontal asymptote. In graphing general rational functions, it involves finding possibly more vertical asymptotes, but still at most one horizontal asymptote. The difference between simple rational functions and general rational functions is in simple rational functions, the functions that are in the numerator and the denominator of our rational function are never larger than first degree equations. So they're linear equations or they're constant equations. In general rational functions, they can be quadratic equations or cubic equations or higher. Now there are some very simple steps to go about graphing general rational functions. We're going to begin by finding the x-intercepts, which are the zeros of the function in the numerator. We're going to find vertical asymptotes, which are the zeros of the function in the denominator. And we're going to follow a set of rules to find out if there is a horizontal asymptote, and if so, what is it? And we do this by comparing the degrees of the polynomials that are in the numerator and the denominator. So if the numerator has a smaller degree than the denominator, y equals 0 is the horizontal asymptote, which would be the x-axis. If the degrees in the numerator and the denominator are equal, then you can find the equation for the horizontal asymptote the same way you did in simple rational functions. It would be y equals the ratio created by the leading coefficient in the numerator divided by the leading coefficient in the denominator. And if the degree in the numerator is greater than the degree in the denominator, there is no horizontal asymptote. So let's go through some examples. In this particular case, you can see that I have a first degree equation in the numerator and a second degree equation in the denominator. So I begin by finding the zeros of the function in the numerator. This will allow me to find the x-intercepts. I set the function to be equal to 0, and then I solve for x. Okay, so I found a single x-intercept at x is equal to -1/4. Now I'm going to find the vertical asymptotes, and I do that by setting the denominator to be equal to 0. And if I solve, there are a couple of ways I could solve, but x squared will be equal to 1, and so x will be equal to plus or minus the square root of 1, which is plus or minus 1. So I have two vertical asymptotes. That makes sense. I had a second degree equation. It will have two solutions. The vertical asymptotes will be at positive and -1. And the last thing I want to find out is about my horizontal asymptote. My degree in the numerator is smaller than the degree in the denominator, so y equals 0 is my horizontal asymptote. If I want to go ahead and graph this, I know -1/4 was an x-intercept. I have asymptotes. As a matter of fact, I'm going to expand this out a little bit. I'm going to do a half per mark. All right, so this is at 1 and -1, and I have a horizontal asymptote here at y equals 0. Okay, so if we want to label those, this is x equals 1, this is x equals -1, and this is y equals 0. Okay, so now the vertical asymptotes have divided the x-axis into three parts. There's a section there, a section there, and a section there. In order to graph this, I'm going to have to do an input-output table for each section. Okay, so what I'm going to go ahead and do now for section, I'm going to start with section 2 in the middle. And I've already got a point here, -1/4, 0. And what I'm going to try to check is what happens at 0 and what happens at 1/2 and what happens at negative 1/2. I think that will give me enough information to be able to define the graph here in between the vertical asymptotes. So when I plug 0 into this equation, I'll have 0 plus 1, so that's 1, over 0 minus 1, that's negative 1, so negative 1. So it'll be right about here. I'm sorry, every 2 spaces, so it'd be right about there. Okay? And when I plug in 1/2, 4 times 1/2 is 2, 2 plus 1 is 3, and 1/2 squared is 1/4, 1/4 minus 1 is negative 3/4. If I then invert and multiply, that's going to be negative 4. So at 1/2, I'd be at negative, let's see, 1, 2, 3, 4, all the way down here. And when I have negative 1/2, 4 times negative 1/2 is negative 2, and negative 2 plus 1 is negative 1. And I'm going to get the same denominator. Negative 1/2 squared is also 1/4, and 1/4 minus 1 is negative 3/4. And so this will be 4/3. So 1 and 1/3. So over here, there's 1, and up here would be about 1/3. So our graph is going to come in along this asymptote, pass through this series of points, and exit along the other asymptote. Okay, if I move on to section 1 and I do an input-output table, I'm going to pick values to the left now of this vertical asymptote. So that's at negative 1. So I might pick something like negative 2, negative 3, negative 4, something like that. So negative 2, negative 3, negative 4. And when I plug negative 2 into my function, I'll have 4 times negative 2, which is negative 8, plus 1 is negative 7. And negative 2 squared is 4, and 4 minus 1 is 3. So I'll have negative 7/3 over here. When I plug negative 3 in, 4 times negative 3 is negative 12, plus 1 is negative 11. Negative 3 squared is 9, minus 1 is 8. So I have negative 11/8. And when I plug in negative 4, I'll have negative 15 over, let's see, 16 minus 1 is 15. So I'll be at negative 1. So if I go ahead and plot these, at negative 2, that's here, we would be at negative 7/3. So there's 3/3, 6/3, 7/3 is about there. And at negative 3, I would be at 11/8. So it's just about 1.5. So it's right around in here, a little less than 1.5. And here we'd be at negative 1. So I believe it comes in along here, goes through these points, and goes out along the other asymptote. Okay, and then I'd want to do the same thing over here for section 3. If I go ahead and in section 3 do an input-output table. Now I'm going to be picking values to the right of 1, so probably 2, 3, and 4, much like I did on the other side. And I'll have 8 plus 1 is 9, and 4 minus 1 is 3, which is 3, so I'd be at 2, 1, 2, 3, all the way up here. I'll have 12 plus 1, which is 13, and 9 minus 1 is 8, 13/8, so that's about, again, a little more than 1 1/2, so 1 1/2, a little bit more. And when I plug in 4, I'll have 16 plus 1, which is 17, over 16 minus 1, which is 15, so it's just a little over 1. here I'd be a little over 1. And over here it looks like I've got the same basic shape that I have in section 1. Okay, so this is how you graph a general rational function. Find the vertical asymptotes, horizontal asymptote, and x-intercepts, and then go ahead and create an input-output table for each of the sections of the x-axis that have been defined by the vertical asymptotes. We have 3 basic scenarios here in terms of the variation lies in determining the horizontal asymptote. So as we go through, when m is equal to n, I'm going to be using the ratio of the leading coefficient, in this case -4 in the numerator, and the leading coefficient, in this case 1, that is in the denominator. So y is equal to -4 is my horizontal asymptote. My vertical asymptotes can be found by setting the denominator to be equal to 0 and solving. So this is going to be x plus 4 times x minus 4 if I factor it. So my vertical asymptotes will be x is equal to 4 and x is equal to -4. And for x-intercepts, if I set the numerator to be equal to 0, x equals 0 will be my x-intercept. So I'm going to go ahead and move to the next slide and put these items into my graph. So I'm going to put my vertical asymptotes in first. 1, 2, 3, -4 and 4. 1, 2, 3, 4. My horizontal asymptote was at y equals -4. Okay, and I had an x-intercept at x is equal to 0. So right there at the origin. Now if I want to do an input-output table, I'm going to go ahead and try in section 2. So section 1, 2, 3. I'm going to start with section 2 again. It's just my preference. I like to start in the middle. I'm going to start by doing 2 and -2 just to sort of see what I get. And what's nice, I'm sorry, 2 and -2, not -3. What's nice in a function like this, where you see I have x squared in the numerator, I have x squared in the denominator, and nowhere do I have x to an odd power. What's nice about that is if I plug in +2 and -2, because it's going to be squared, the output is going to be the same for each of these. So it can save me a little bit of time, and it gives you a little bit of a shortcut in filling out your input-output tables. So if I plug 2 in, 2 squared is 4 times -4 is -16. And down here, 2 squared is 4. 4 minus 16 is -8. -16 divided by -8 is 2. And I'll get exactly the same thing when I plug in -2. So there's 2 and 2. So it looks like this is going to be a parabola that comes in here, changes directions there, and heads back out. I know it's going to be symmetrical because if I plug in -1 and 1, again, I'm going to get the same outputs. Okay, so that's section 2. If I move on to section 1, nice thing about section 1 and section 3, you can see if I pick negative x values for section 1 and I select their positive counterpoints in section 3, again, those outputs are going to be the same because x is squared everywhere it exists in this problem. So if I take, say, -5, -6, so -5 is relatively close. Maybe I want to space out a little more, maybe -5, -7, and -9, just to get a little distance between my points. And then over here in section 3, I'm going to pick their positive counterparts, 5, 7, and 9, because I know the outputs will be the same. So when I plug 5 in and square it, I'll get 25 times -4 is negative 100. And when I plug it in here, I'll get 25 minus 16, which is 9. So this is a little over negative 10. Okay, so that's going to be down here, a little more than negative 10. When I plug in 7, negative 7 squared is 49 times negative 4 is about 200. It's 198, right? But it's 196. And then 49 minus 16 is 33. So you can see this is going to be about approximately negative 6. I'm estimating because we're graphing, so we've got some level of estimation going on anyway. So about probably a little bit below that, negative 6. And then when I plug in 9, negative 9 squared is 81 times 4 is 324, negative 324. And 81 minus 16, 81 minus 16, 65. So this is going to be a little more than, or just about, negative 5. So as I move out here, I'm really close to negative 5. So again, this looks like it's a parabola here. And I'm going to get the same values for these. So I can go ahead and pop these guys in. And there's my graph. Okay, so take advantage of the fact that when x is only to even powers, the output from a negative number or its positive counterpart are going to be the same output. It'll save you a bit of work. The last case we could have here is when m is greater than n, and in that case there is no horizontal asymptote. So no horizontal asymptote. If I want to find the vertical asymptote, I set my denominator to be equal to 0. And if I divide by 2, x equals 0 will be the vertical asymptote. If I want to find my x-intercepts, I set the numerator to be equal to 0. And if I factor this, I know that my binomials have the same sign and they're both minuses. I'll have x here and x here. And factors of 20 that add up to be 9 are 5 and 4. So my x-intercepts are 5 and 4. If I move forward to go ahead and finish graphing this problem, I know I have intercepts at 1, 2, 3, 4, and at 5. I know that I had a vertical asymptote at x equals 0, so that's right here on the y-axis, and I have no horizontal asymptote. The vertical asymptote has split the x-axis into two parts, positive numbers and negative numbers, and I'm going to go ahead and do an input-output table for section 1 and section 2. I'm going to start with section 2 because I already have 2 points over there. And what I want to find out is what happens here close to the asymptote and what happens out here a little further away. And if I want a little more detail, I might want to check what happens between my two x-intercepts. But for now, I'm going to plug in 1 and see what happens. And then let's see, 5, 6, 7, 8. And I'm going to plug in 8 and see what happens further out here. So when I plug 1 in, I'll have 1 squared, which is 1, minus 9 plus 20, divided by 2 times 1, which is 2. So 1 minus 9 is negative 8. Negative 8 plus 20 is 12, and 12 divided by 2 is 6. So at 1, I'd be at 1, 2, 3, 4, 5, 6. And when I plug in 8, 8 squared is 64, minus 9 times 8, which is 72, plus 20, all over 16. So 64 minus 72 is negative 8. Negative 8 plus 20 is 12. And 12 divided by 16 will be 3/4. So if I go out here to 8, I'm going to be about there. So what it looks like to me is this comes in along here, passes through these guys, and then heads out in this direction. Now if I wanted more detail, I might check an x value here between the two x-intercepts, but for our purposes in graphing, I would suggest you do basically this and then double check with your calculator to see if you've found enough information for the graph. I don't really want you to spend ridiculous amounts of time creating input-output tables. On the left side here, I'm going to again check close to the vertical asymptote. I want to check a little ways away, so maybe -3, and then a little further away, -7, and hopefully I'll get a sense of the shape with these 3 points. So when I plug -1 in, -1 squared is 1, minus -9 is plus 9, plus 20, all over -2. So this is 10, 30, -15. And when I plug in 3, I'll have 9 plus 27 plus 20, all over -6. This is 47, 56 divided by 6, -56 over 6. So that's going to be, what, 28 thirds, -28 thirds. That's a little over 9, right? So that's approximately -9. So if I start putting some of these points in, 15's way down here, it's off my graph. If I go over to 2, 3, and I come up to -9, right about there, just a little below -9. And when I plug in 7, I'll have 49 plus 63 plus 20, all divided by -14. So 83, 120, 132 divided by 14. That's between 9 and 10. Right? So I do that again is approximately -9. So if we got to 4, 5, 6, 7, right about here. I'm going to assume we have a similar shape here where this is going to come up here, head back down, and go back out. Again, you should be checking with your calculator to see if your assumptions about the shape of the graph are valid. Okay, so those are the 3 different cases that you would need to graph. Again, the point of this exercise is for you to be able to follow the rules, to select appropriate in and out points, to attempt to define the shape of the graph. Use your calculator to double check to make sure that your assumptions are valid. Sometimes these things make very sudden turns that are hard to predict. So go ahead and work through this. This will be minimally represented on the test, but you will certainly have it on the quiz next class. Thanks.